In these notes, we're going to investigate a concept called Lewis dot structures, where we can represent covalent bonding using dots. So let's get started. All right, our first question is, how can Lewis dot structures help us figure out covalent bonds? Now, in last class, in the last notes, we were talking about covalent bonds in which atoms share electrons with each other. And we were drawing out different structural formulas for covalent molecules, right? So you were drawing out the little H's and the C's and hooking them together with little lines that represented the bonds. So we, found out that hydrogen can make one bond, and oxygen can make two, and nitrogen can make three, and carbon makes four bonds. But how do we actually know that those rules exist? So this is what we're going to investigate here. Lewis dot structures actually show you how the valence electrons are arranged so that we know that carbon will always make four bonds and nitrogen will always make three bonds. So Lewis dot structures are named after this man right here, named Gilbert Newton Lewis. All right, so he was a scientist, and he figured out this way to easily keep track of valence electrons in covalent bonding. So let's take a look at Lewis dot structures. All right, so first off, Lewis dot structures are drawings of atoms with dots to represent their valence electrons. So we're not actually drawing out the protons, neutrons, and electrons, but we are representing the atom with their chemical symbol. Okay, so for example, if we do carbon, we'll put a C for carbon, and we will represent its valence electrons using dots. So carbon has four valence electrons, so we will put four dots around carbon. We start at the top, okay, and then we add one on each side until you have all of the dots for that particular atom. So when you're making a Lewis dot structure, you always start with the first dot on the top, and then you add a dot on the right side, then one on the bottom, then one on the other side, and if you have more than four, then you'll start pairing them up on each side. So let me show you an example of that one. So here nitrogen, if you look, is in group 5A, so he has five valence electrons. So what we're going to do is we're going to put one dot on top, and we're going to go around and put one dot on each side till we get four, and then with his fifth one, we're going to pair it up with the one on top. All right, and so he's going to have one pair of electrons and three kind of lonely electrons. All right, so we put one dot on each side first, and then you pair up the extras. All right, one of the cool things about Lewis dots is that they show you the paired versus unpaired valence electrons, and that's important because the paired electrons will not make bonds, but the unpaired electrons will form bonds. So that's how we know that nitrogen, for example, up here has three unpaired electrons, so he is going to make three bonds, just like the honk 1, 2, 3 rule says. So as another example, here's oxygen. Oxygen has six valence electrons, so we're going to put one dot on each side, okay, for four, and then we're going to pair up the last two. So we can see that we have two paired electrons, okay? These guys are paired, and therefore they do not make a bond. And he also has two unpaired electrons that do make bonds. So that's why in the honk 1, 2, 3, 4 rule, oxygen always makes two bonds, because he has two electrons there that are lonely and want to get paired up by making a covalent bond. All right, our second question has to do with the octet rule. Octet refers to the number 8. And if you recall, in ionic bonds, 8 was that magic number for bonding. So the metal atoms wanted to lose their valence electrons so that they exposed the shell right underneath it, which has 8 valence electrons. And also the nonmetals wanted to get or grab an enough electrons to make 8 total. So 8 is that magic number when it comes to bonding. And it's the same thing with covalent bonds. Nonmetals, when they hook up, want to have 8 electrons around them. All right. Now the only exception here is hydrogen. Hydrogen is a little guy. He can only, hold up to 2 electrons. All right. So he only wants 2, but all the other ones want 8. Just like those noble gases. So, in fact, noble gases don't form bonds because they already have 8 electrons around them. So if we take a look at argon, argon has 8 valence electrons. So if we do the Lewis dot structure for argon, we would have 1, 2, 3, 4, 5, 6, 7, 8. And you can see all of the electrons are paired, so they're not going to make any bonds because they don't have any lonely unpaired electrons. All right, so atoms that have lonely electrons in their valence shell, so atoms that don't have a pair within the orbital, are going to be very reactive. They're going to want to seek out to make bonds in order for them to become stable. So once they become stable, when they get 8 valence electrons around them, whether they are their own valence electrons or they are electrons that are being shared with another one. So let's take a look at an example. We're going to take a look at carbon tetrachloride. So we're going to put carbon, since he makes the most bonds, we're going to put him first. And carbon has 4 valence electrons, so let's put the dots for carbon. And Cl, okay, we're going to hook up Cl's all around him. Carbon can make 4 bonds. There are 4 Cl's that need to be in this compound, so we're going to hook up a Cl on each of these 4 sides. Now, chlorine has 7 of its own valence electrons, so we're going to put a valence electron on each side. 1, 2, 3, 4. This one right here just made a bond. Okay, right here in the middle, we just made a bond right there with that sharing of those 2 electrons. All right, so that's 4, 5, 6, 7. All right, and so we're going to do that all the way around. Okay, so it's going to look like this, where we've got one of carbon's electrons, lonely electrons, pairing up with the only lonely electron that chlorine has to make 4 different bonds here, to make carbon tetrachloride. So as soon as we have 8 electrons around all of our atoms, we are nice and stable. So if we count up all the ones around each chlorine, we've got 2, 4, 6, 8. If we count up all the ones around carbon as well, okay, again we have 2, 4, 6, 8. So you have to have all 4 sides filled with 2 valence electrons each in order to become a stable, legitimate, covalently bonded molecule. All right, our third question is how many covalent bonds will nonmetals make? We can figure out how many bonds they'll make by doing Lewis dot structures. We can also figure it out using a very simple math equation. All right, so here's the simple math equation. The number of bonds that a nonmetal will make is, again, 8, that magic happy number, minus the group A number, which, if you remember, is the number of valence electrons. So if we take 8 and we subtract the number of valence electrons, that's going to be how many bonds that nonmetal is going to make. So let's take a look at an example of sulfur. And I'm going to show you how this equation matches up with what we know with the Lewis dot structures. All right, so for sulfur, the number of bonds is going to be equal to 8 minus his group A number, the number of valence electrons. And sulfur's in group 6A, so he has 6 valence electrons. So his number of bonds is going to be 8 minus 6, which is 2. So sulfur will make 2 bonds. So let's put his dots down and see exactly why. All right, so we have 1, 2, 3, 4, 5, 6. All right, and so we can see here that we've got 2 lonely unpaired electrons that are going to make bonds. So again, he has 2 lonely electrons in its valence shell that want to be paired up. All right, they're not going to be, happy or stable until they find a pair. So let's pair these guys up with a couple of hydrogens. All right, so we've got sulfur here. We're going to hook them up with a couple of hydrogens. Hydrogen, remember, has one valence electron, so he's going to be able to come and share his dot, okay, or his valence electron with one of sulfur's lonely valence electron. And so we can do that. We'll add two hydrogens to this sulfur to make two bonds. So we've just made, H2S. So here again, sulfur is going to share its lonely electrons with hydrogen's lonely electron to make a covalent bond so that both atoms are now happy. So as kind of a little, recap here, we've got sulfur here. He's got two sides with lone pairs or paired up electrons that are not involved in bonding. And he's also got two unpaired electrons here that were able to make a covalent bond. So now that he has a total of 8 shared electrons all around him, so now that he is happy and stable. So these bonded electron pairs are involved in actually making a bond between hydrogen and the sulfur atom. So if we take a look at each of the atoms individually, we will see that they have reached their magical happy number in order to become stable. So sulfur around him has 2, 4, 6, 8 electrons, and each hydrogen has 2 electrons, and so that makes each of the atoms happy and stable, and so we've got a legitimately good covalent compound here. All right, our fourth question in these notes is, how can Lewis dot structures represent multiple bonds? Because from the honk activity lab that we did that sometimes carbon and oxygen and nitrogen can make more than just a single bond. They can make double bonds or triple bonds. So here we're going to see how we represent that using Lewis dot structures. All right, first let's investigate single bonds. In a single covalent bond, that means that 2 electrons are shared between each atom. All right, and remember, we have to have, when we make a bond, we have to have 8 electrons around each atom after it bonds, so it's stable again. So let's take a look at an example. All right, we're going to hook up 2 fluorine atoms together. 2 fluorine atoms are nonmetals, so they're going to have a covalent bond, so they'll share. So let's do the Lewis dots for fluorine. We have 1, 2, 3, 4, 5, 6, 7. Okay, in that one, and then let's hook it up with another fluorine right next to it. Okay, and so here are his dots. 1, 2, here's our bond, 3, 4, 5, and then 6, 7. So here we see that we've got a bond here between 2 atoms, and each of these fluorine atoms now has 8 electrons around it now that they're sharing those 2 there in the middle. So that's how we represent a single bond in Lewis dot structures. Let's take a look at double bonds. So in a double bond, we've got 4 electrons being shared in between 2 atoms. So instead of having 2 dots, we're going to have 4 dots in a double bond. So let's see how this works out with O2. Okay, so our example will be O2, the molecule O2. So let's take a look. Let's do the Lewis dots for one of the oxygens. Oxygen has 6 valence electrons, so we're going to put 1, 2, 3, 4, 5, 6 around that one. And we're going to now do another oxygen, and we'll put 1, 2, here's our first bond, 3, 4, 5, 6. Okay, now we see here when we put the dots around oxygen, okay, we have 2 lonely electrons still that are not paired up. Okay, and that is a big no-no. We always want those electrons being paired up. Now, and according to our formula over here, there's no other hydrogens or no other elements in this compound. So we have to do something with those lonely electrons. So that's where we're going to take them and we're going to put them in the middle. Okay, we're going to pair them up in the middle to make a double bond there in the middle. So this is what it looks like. So here we have what represents a double bond between these two oxygens. So here we've got 4 electrons being shared between the two atoms, and that is a double bond. And again, we've got, if we take a look at each of the oxygen atoms separately, you'll see that they both have 8 electrons around them. The 4 of them in the middle between them, and then the other, each of them have 4 of their own, or 2 pairs of their own. All right, so that's how double bonds work. If you have any leftover electrons, okay, unpaired electrons, they have to go in the middle to make a double bond. All right, let's take a look at triple bonds. All right, just as you guessed it, triple bonds means that there are 3 pairs of electrons being shared, or 6 total electrons shared between 2 of the atoms. So in this example, we're going to draw out the molecule N2, or nitrogen gas. So let's draw out each of the N's with their respective number of valence electrons. So nitrogen has 5, so we're going to do 1, 2, 3, 4, 5, and then we're going to hook it up with another nitrogen right next to it. Okay, and it has 1, 2, there's 1 bond, 3, 4, and 5. All right, so we see here that we've got 1, 2, 3, 4 unpaired electrons within these 2 nitrogen atoms, and that is, again, is a big no-no. We never want unpaired electrons around our atom. So what we're going to do is that we've got equal numbers of unpaired electrons on both sides, so we're going to take all of these, put them in the middle, okay, and pair them up in the middle to make a big triple bond. So this is what it looks like over here. All right, so here's our nitrogen with our triple bond over here. So we've got this bond here in the middle, 6 shared electrons, and that's going to make a triple bond. And then we see here that we've got each of the nitrogens has 1 lone pair in it, or 1 paired up electron by itself. And if you notice, I moved them from the top over to the sides here because remember, electrons are negatively charged, and so they're going to want to be, the electron pairs are going to want to be as far apart from each other as possible. So if there's a bunch of them in the middle, all the rest of them want to be, you know, on the sides as far apart from each other as possible. Now, again, if we take a look, if we verify with our octet rule, we've got 8 electrons around each nitrogen atom, 6 that are being shared in the middle, and then 2 of its own on either side. So that's how we represent a triple bond in Lewis dot structures. All right, our last slide is just going to be some strategies to help you create Lewis dot structures from scratch. All right, again, here's our last slide with strategies that you are going to use tomorrow when you're creating Lewis dot structures for different compounds. So you're going to identify the central atom before you even start. It's usually carbon or any of the elements from group 4A. It's usually not oxygen unless there is no carbon. Okay, so if there's not a carbon or somebody from group 4A, then it'll be, you know, the next atom that can make the most number of bonds, which will be either oxygen or anybody from 5 or 6A. It's never going to be hydrogen or any of the halogens from 7A unless there are only halogens in the compound or hydrogen hooked up with a halogen. Otherwise, you never start with hydrogens. After that, you'll draw out your Lewis dot structure for each of the atoms and combine them all together. All right, you check to see if all atoms satisfy our octet rule, meaning that they have 8 electrons around them, including the ones that they're sharing. If not, if you have lonely electrons, that means there must be multiple bonds there. So that means you have to hook them up to make double bonds or triple bonds. And then last but not least, you always want to double check yourself, and the best way to double check is the honk 1, 2, 3, 4 rule. All right, so you can use that to check yourself. All right, so tomorrow we're going to do lots of Lewis dot structures, from single bond to double bonds, some with triple bonds, and so be ready with these notes tomorrow handy, so that you guys can, you know, go use these strategies when you're doing those Lewis dot structures. And then I also wanted to, award those that are actually doing the notes on time. So we're going to have another extra credit opportunity. So tomorrow you can come and grab one of my sticky notes, write your name and the keyword Lewis dot. Okay, so keyword Lewis dot for some extra credit bonus points for actually watching these notes and listening to them. All right, we'll see you tomorrow.